Are there any questions on the homework? I changed it from a June due date to maybe today. Any questions? I posted in XYZ today, until I make the assignment for today, it'll be on the very top panel. It's also on the calendar. I think it's under the word practice, like 3 problems. I think I could have had better problems to choose from on the online homework. And so I just put 3 more problems out there for you to practice. They're not going to be graded. But, you know, trig substitution, it can be a little bit tricky all the way through, really. I mean, the details for the trig sub and then the dealing with the trig integral you get. And if it's an indefinite integral, you know, when we're done, like working our way back to the original variable, all of that takes effort on our part. And every part of it needs to be right if we're going to get the right answer. So take a look at the top panel. Again, there's no due date. I strongly encourage you to be familiar with those problems before our next exam. And you know, I can let you read it, but I also encourage you, like, this is just a good principle for being a college student. Like, if you get the feeling that your professor, whatever the subject is, makes up things for you to do, that's not like in the textbook, or in our case on the online homework, then, you know, if I'm the person who makes up your exams, right, who eventually decides what grade you're going to get. And if I make up work for you to do, you know, you ought to put a red star by it and say, I'm going to focus on this. You went to enough trouble to make it available. And so, you know, maybe we'll get a chance to talk about it. I think I promised you that I maybe at some point would post solutions or at least answers, but not real soon. See if you can beat me there. But maybe by the end of next week, I'll post answer. Just, you know, you need some feedback. Of course, you can always take the derivative. If you're finding an antiderivative, you can take the derivative and see. But sometimes that's about as much work as finding the antiderivative. And it's as fraught with the possibilities of making mistakes. So sometimes I'll do it. I'm a math professor, just for the fun of it. Like sometimes you get an antiderivative, it's like, good grief, that's a bizarre. How in the world could it be true? And so I'll say, well, I'm going to take the derivative and see what happens. And eventually, I can see it all works out. It's pretty amazing. All right. With that said, I'm going to declare that we're done as far as formal presentation with section 3. Okay, you have a homework due today. You have 3 extra problems I created for you, but that finishes. We'll talk about it again before the second exam, but in terms of classroom experience, that finishes section 3. And so we'll move on to section 4. I think I told you on Wednesday, you might find it a little bit easier than section 3. I don't know if that's good or bad. Like, I mean, you want a good challenge, don't you? But we'll see. Are there any questions before we move on? All right, section 4. It's the same general thing. We're looking for antiderivatives. Okay, we learned some things in Calc 1. We're learning more things. Every section of chapter 3 is a new way for us to find antiderivatives by parts, trig functions, right? Various combinations, trig substitution, and now the 4th one. It's probably called partial fractions in the textbook. It's going to take us just a minute before we get to actual partial fractions, but we will. Partial fractions is a technique for integrating, for finding antiderivatives for a certain kind of function. Or what are called rational functions. I think we talked about those in Calc 1. But I'm going to pretend like we didn't. And I'll tell you everything about them that's relevant to the work that we're going to do. Okay? So what is a rational function? Can we abbreviate for section 4? And just so we don't have to write those words all the time, we'll just understand in section 4 that RF means rational function. I won't do it on the test. If I want to say rational function, I'll type it all out, but just for today's class, really. So what is an RF, rational function? It's a real simple thing. It's a ratio. Think of fraction of polynomials. And hopefully all of those words have meaning to you. If you know what ratios are, then maybe you weren't ready to think about them algebraically. And so I told you, they're just fractions. And hopefully you know what a polynomial is. We've been working with them a lot. Polynomials have degrees associated, right? You have linear ones and quadratic ones and third degree and on and on. So a rational function has 2 degrees associated with it. The degree of the polynomial in the numerator and the degree of the polynomial in the denominator. Okay? So let's let D be the degree in the denominator. You see what I did? D for denominator. And what shall we use to symbolize the degree of the numerator? What do you think? X? What do you think? It's okay to say things out loud. Okay with that. Some brave person, Scott.
Would it be an exponent?
Okay, so I want a symbol for it. It's actually, it is an exponent. It's the largest exponent that occurs, right? That's what the degree is. So if I call the one in the denominator D, let's call the one in the numerator N. Wonderful. If N is bigger than or equal to D, if the degree in the numerator is as big or bigger than the degree in the denominator, the RF, the rational function, is called improper. Otherwise, it's called proper. I hate it that they call it improper because it sounds like there's something wrong with it. And maybe there is. We'll decide in the end. But it's a perfectly good function. You've done this sort of thing before in, I don't know, 3rd grade. What's an improper fraction? Will.
Fraction that's greater than 1.
Pardon?
A fraction that's greater than 1.
Yeah, correct. I might say it a different way. Somebody want to take another try at it?
When the numerator is larger in magnitude than the
Yeah,
denominator.
which would make it bigger than 1, William. So you're both exactly right. And I don't know. I'll pick my favorite one, 21/8. And you learned way back in the day to like to take as many 8s out of it as you can. Right? Like if I took 16 of them out, I could convert that to a 2, and then I'd have some left over. 5 of them. Right, and you learn how to do this. So we start with something that we called improper. Terrible name for it. And we get something that we can think of this as the whole part, and then we get this proper thing left over, which the number is less, the numerator is less, like Scott said, and the fraction is less than 1, like Wilson. Okay, we're going to do exactly that sort of thing for an improper rational function. We're going to break it down into a whole part, which would be a polynomial for us, an ordinary polynomial, not a ratio, not a fraction, and then a rational function left over. That's proper. The degree of the numerator will be strictly less than the degree of the denominator. Okay? So this is kind of a good model, and watch the video, you can't see it. So I went outside my lines. So if you're watching the video, just pause and take a look at what I did, and then you can catch back up with this. All right. Partial fractions is a technique that only works on proper rational functions. Oh, too many words that start with P. So this is the new technique, partial fractions, and it only works, it only gets us good answers on proper rational functions, or F's. And use our abbreviation. Okay. So I said it only works, it only gets us good information. Unfortunately, if you apply the technique to an improper one, the technique's never going to break down. You're going to think, oh yeah, I'm doing this work and it's wonderful and it's going to get me the right answer, but it's not. You have to start with an improper, with a proper one you learn the technique. So if we have an improper one, then we need to do what we learned how to do over here in 3rd grade, how to decompose it into a whole part, which for us is a polynomial, plus a proper rational function. And maybe you can think about how you did that. So let's try this. Write the improper That's improper, right? The degree of the top is 2. The degree of the bottom is
1.
Improper. So what I'm going to do is write it as a whole, which is a polynomial, an integer in 3rd grade, but a polynomial here, plus a proper. RF, rational function. And we do that by long dividing. It's how we would do this problem if we couldn't do it in our heads. And long divide. And hopefully you remember, or at least you can refresh your memory as to how we divide polynomials, long divide. This is a pre-calculus technique. I'm going to talk my way through it. If some of the steps seem a little bit fuzzy, you can work it out later. And by working it out, I mean find out how to do it, or come and talk to me, or go to Math Lab. They can help you. Okay. So I'm not going to spend too much time on it now. So first thing I say is, how many times does x go into x? That is what? What do I need to multiply x by to get me x squared? And the answer is x. And then we multiply out. That comes down here, x squared plus 2x. And then we subtract. If we did it right, the first step right, those x squareds are going to cancel. And sure enough, X squared minus X squared is 0. And then I get X minus 2X, so we're subtracting this whole thing here, and that's going to give me minus X. And then I got a 1 that's coming along for the right. So if we took an X out, and what we had left over, it's like that X is, didn't write it, they didn't write it out. That X is playing the role of the polynomial, and we have a rational fraction left over. Unfortunately, it's not yet proper because it's this polynomial minus X plus 1 divided by X plus 2. That's the remainder we have. And the degrees are the same. They're both 1. Well, we need the degree to be strictly less than. And so we'll divide again. X goes into minus X minus 1 times. Multiply again, minus X minus 2. Subtract. So this guy is the first remainder. You think of him as a polynomial. The same degree as the thing we're dividing. So we need to go again until finally we get a polynomial down here. It doesn't look like a polynomial, but it is, whose degree is less than the thing we're dividing by. Now, what we've shown is the original improper rational function, x squared plus x plus 1 divided by x plus 2 is the same as x minus 1 polynomial, the whole part, plus 3. I shouldn't have written the integral first. I should have written the algebraic fact we discovered. And just like back in 3rd grade, we start improper, get a whole thing, which, because we're not in 3rd grade anymore, it's not an integer, it's a polynomial, plus we get a proper. Very close analog. Julian. 1 minus negative 2. 1 plus 2. We multiplied. We took the minus 1 and we multiplied. Minus 1 times x is negative x. Minus 1 times 2 is negative 2. Okay? And then we subtract. It's exactly what we did way back when. Right? How many times does 8 go? Twice. Multiply, just like we did. Subtract, just like we did. There's the 5. And for arithmetic, here I am off the screen again. For arithmetic, for fractions, we stop whenever this number is less than the thing we're dividing by. Whereas for polynomials, it's when the degree is less. All right. Any other questions? Make these guys dizzy. Okay, so we're in calculus. We're not in 3rd grade working with improper fractions. What in the world does it do us? Well, before today, if I say, what's the antiderivative of this function? You guys would probably say, we don't have any idea. We've never learned a technique for it. No simple substitution will do the job. Like, we don't know what to do. But we recognize it's improper. We do the work. And what do you think? This, for every single x value, this should be a plus 2, sorry. For every single x value for which this is defined, which is every number except for negative 2, these are the same function. So if this function has an antiderivative, it's going to be the same up to a constant, possibly, as this one. They're the same function. And if I look over here, like, how hard is that antiderivative? You better say really, really easy. Here it is. 1/2 x squared minus x plus what? Someone tell me.
I don't know the answer. derivative of c of x.
Well, wouldn't you separate the fractions and it would be the antiderivative of 3 over x
Which is
ln of 3
3 ln
for x.
plus 2. That's fast. Okay? You agree with me? Because our super quiet class, I can really tell what to think. How many of you noticed that I wrote x minus 2 when I should have written x plus 2? Yeah, be sure and let me know. Like maybe I'll hand out gold stars or something if you can find a mistake. Probably most of you wrote plus 2 in your notes, I hope, without even looking at them. Good. All right. Any questions? So we've shown how recognizing an improper rational function whose antiderivative we don't really have a method for unless we can long divide, break it into the whole plus the piece, okay? Unfortunately, well, that's certainly true. And I said that partial fractions only works on proper. So, you know, if we start with an improper, then we have a polynomial, which is trivial to find the antiderivative. And then the new technique is going to tell us how to handle this piece. And if it's 3 over x plus 2, we don't need a new technique, right? We learned it way back in Calc 1. So what's going to happen for us is that proper part is going to get more complicated. And that's where the new techniques. So far, I haven't shown you anything at all about the new technique, partial fractions. I've shown you how, well, we need to talk about proper versus improper because it only works, as I've written here, the new technique only works on proper rational functions. So 100% of the time, if we have an improper one, we've got a long divide. Okay, I mean, if we don't already know an antiderivative, we've got a long divide, the polynomial piece, trivial, if I could say, the antiderivative, and then we're stuck with the proper one, and that's where the new technique comes in. If it looks like this, we don't need it. We can write it out, we're done. But this piece is going to look more complicated. All right. Any questions? Scott?
You said it should have been x minus 2?
No, when I first wrote this out, I wrote a -2, right?
Oh.
Yeah, which is just careless on my part. And I discovered it when I was getting ready to tell you that except at -2, these are the same function. I mean, they're undefined at -2, but then I said, well, this one's not. Oops. Wait a second. Now, those are the same functions for every x value except for -2, and they're undefined at -2. All right, so partial fractions, the new technique. I mean, really, we could have had this discussion in Calc 1, right? When we're learning basic antiderivatives, as long as we wouldn't let this possibly difficult part get too complicated, like this example, nice and easy. But like I said, I use kind of a word I have to be careful with, like I think I said trivial, the polynomial part, the antiderivative of it. I've been teaching calculus for 41 years, maybe a little bit more. And I think I have not yet seen a student who couldn't find an antiderivative of polynomial. So that makes it trivial. But if it gets more complicated, then, you know, I've seen lots of variations. Some of them not real great. Partial fractions. Turned out there are 4 cases. We're only going to talk about the 3 of them. But theoretically, there are 4 cases. And the cases depend on how complicated our original denominator is. Remember, our technique, we're ready to learn this technique, which means we have a proper rational function. Polynomial over a polynomial, the degree of the numerator is less. Okay, that's when we launched the technique. The cases depend on the nature of the denominator. In particular, I have to write it in factored form. To start with, a lot of the problems, it will be factored for us. But if it's not, then we have to factor. Okay. The fundamental theorem of algebra says that every polynomial with integer coefficients can be factored into linear and irreducible quadratic polynomials. So it says take any polynomial in the world, no matter what its degree is, the coefficients are integers. Then it's possible to factor that into linear factors, x plus 2, 2x plus 5, those are linear factors, and what we call irreducible quadratic, quadratics that can't be factored in the real number system. I'll write one up here. The one we see most often is probably x squared plus 1. You can't factor that in the real number system. Okay, that's an irreducible quadratic. If you remember back to our quadratic equation theory, a quadratic polynomial is irreducible if the discriminant b squared minus 4ac is a negative number. Does that mean anything to you? B squared minus 4ac, have you heard that before? Yeah, it's the thing that's under the square root. So if that's negative, the solution is not a real number. And we only care about real numbers, right? The graph is a parabola of a quadratic. And if it's never equal to 0, it never crosses the x-axis. And it never gonna equal 0 across the x-axis if b squared minus 4ac is a negative number. Okay, so that's how we tell. Now, for us, most of the time, the irreducible quadratics are going to be sort of obvious, you know, plus 4, that sort of thing. But if we're not sure, and we ought to do at least one before we're done, where it's not of that simple form, just for the experience. We'll see. Now, the fundamental theorem of algebra, the way that it was proven, probably maybe by a guy named Galois, a Frenchman who, a fascinating story. I'd love to see somebody make his life into a movie. He was a brilliant, brilliant man, maybe on pace to be one of the greatest mathematicians ever. We teach a class here that has a chapter, this is like 250 years later, called Galois theory, like just digging into how he added to the knowledge in that area. And he died when he was like 18 years old, and he didn't do any math the last year of his life. Fascinating story. The way they prove the theorem, the fundamental theorem, is not by showing us how to find the factors. That would be what we call a constructive proof. Like, you can always do this, and here's how you do it. Instead, what he did was assume that it cannot be factored into linears and irreducible quadratics, and then you arrive at a contradiction. Therefore, your assumption is wrong, and we have a theorem. Anyway, we don't really need to worry about all of that. It's a fascinating, but Galois theory, actually the fundamental theorem of algebra says, I haven't written it on the board yet. Every quadratic, every RF, every polynomial can be factored into linear and irreducible quadratics. You can use that fact, even though we can't prove it, to determine how many cases there are. We take the polynomial in the denominator and we factor it. And we know we can get linears and quadratics, irreducible quadratics. And then depending on what happens there, we're going to come up with these cases. Case one. Yeah, I said right here. Depending on the denominator. Case one. The denominator can be factored into distinct linear factors. Different linear factors. If my denominator is, say, x squared, and that's kind of a trivial case, but notice that is the product of two linear factors, x times x, right? But that's not case one because they're the same factor. Okay? If I had something like x times x plus 2, now those are linear and they're not the same. X times x plus 2, x and x plus 2 are different polynomials. Okay, so that's what I mean. I can get linear ones, all linears, and they're different. Okay. So before I launch the technique, let's just do a simple little example. Let's take a function like 2 over x plus 2 plus 4 over x minus 3. And let's add those fractions up. So we find a common denominator. The factors, the denominators have no factors in common, so the common denominator is simply the product. We multiply the numerators by the other denominator, just like we learned way back when. See if that makes sense to you. It's just the rules for adding fractions, nothing sophisticated. And let's multiply. We'll multiply out the numerator and denominator. Easy to do. Just high school algebra. And then we end up with this. The thing we started with, 2 over x plus 2 plus 4 over x minus equals 6x, right? And what?
Plus 2.
Plus 2 divided by x squared minus x minus 6. Now, that's all algebra. This is calculus. Suppose I want the antiderivative. This function right here. How can I find it? Someone tell me what to do. Will.
Break it up into the fractions you had before.
Yeah, we just write it this way. Hopefully, you can look at this and say, the antiderivative is obvious there. So even though we have no tool, other than what we're just talking about today, for finding antiderivatives of this, we can use this algebraic fact. So when I think about antiderivatives, I think, I don't know what to do here. And then I look over here and say, oh, it's easy. And somehow, now, if you think carefully, like we did the problem backwards, I started with the easy part. But the new technique we're learning is how to take something like this, which we don't know the antiderivative for. I've declared it hard, or hara, there we go, hard, and decompose it, break it out into parts so the antiderivative is easy. That's what the technique tells us how. Okay? And so let's just finish the problem. The antiderivative of that thing, who before today we had no clue how to get it. All it is twice the natural log of x plus 2 plus 4 times the natural log of x minus 3. And for good measure, we'll add a c. I've never used XYZ homework for Calc 2 before. You remember when we learned about logs, when you learned about logs, there are all of those properties. There's like 100 ways to rewrite that antiderivative. I hope that XYZ will be super flexible. Sum of logs is the log of the product, right? I can bump these. So this is not important. I hope it will accept this, but for example, and I don't really want to explain this right now, but I could write this whole thing as the natural log of x plus 2 squared over x minus 3 to the 4th power using log property. So just know that there's lots of ways to rewrite it, and we'll hope and I don't know if we'll pray about it literally. We'll hope that XYZ will let us be flexible with our answers. All right. I think we're ready. Now, the technique shows us how to do the decomposition. We're going to start with the thing on the right, whose antiderivative we don't know, and seek a decomposition whose antiderivative we do know. So let's write it like this. We have seeking the antiderivative of f over g, f of x and g of x are polynomials and the degree of f is strictly less than the degree of g. Okay, that's where we are. If that's not true, then we have long divided. We pulled a polynomial out of it, and then we have a proper one left over that it is true for. So we'll just focus on that. It's proper. So for case 1, what we're going to do is factor g. And for case 1, we can factor it into distinct linear factors. If we can't do it, we're not in case 1. Each factor generates a term in the decomposition that we are looking for. Oh, brother blue. See if this one knows. This is the decomposition. Because we took this guy, sort of one piece, and wrote it in 2. If our denominator over here would have had 4 linear factors, we would have 4 terms in our decomposition. Okay? But the only thing that is not obvious, if I start here, is what should these numbers be? 4 and the 2. But is the factors of the denominator are going to get us the denominators respective. And the only question is what are the constants on top? It's sort of balance this whole thing out. So we get a term that has this form. Trying to describe in the abstract is, when we get to a specific example, I hope it'll be like super obvious. This is what we do, but we need a guideline to follow. Of the form, a term of the form, some unknown constant, I'm just going to call it cap A, divided by the linear factor. I'll write it like mx plus b. Recognize that as a line, right? And then we solve for constants, all the numerators. So each factor generates one of those. So if I have 4 factors, I'm looking for 4 constants. We're going to call them A, B, C, and D. Okay. If I have 22 factors, maybe we'll never see one of those. We can hope. I'm going to have 22 constants for me to look for. Okay. And I'm going to just take my 22 factors in the denominator and break it into 22 individual fractions with 1 factor in the denominator, working my way down, and then I have these constants to solve for. I'm going to show you a slick way to solve for the constants. So here's an example. Integrate. Let's say something like x cubed minus 4x over 2x plus 3.
Wait, I noticed something, you said x cubed minus 4x over 2x plus 3.
Did I say it the wrong way?
Yeah, but
I said over when I should have said under.
Yeah.
I apologize.
3 over x cubed minus 4x.
Yeah, if I said it backwards, I wrote it correctly. So on the video or in the classroom, here's the guy we're working. Is it a proper, first of all, is it a rational function?
Yes.
Sure, polynomial divided by a polynomial. Is it proper?
Yeah.
Yeah. First degree, third degree. Top is less. What's the next thing I need to do?
Factor.
Factor the denominator. Now, the way the denominator factors tells us what case we're in. Well, we only know one case. So we better get individual, different linear factors. So let's think about it a little bit. I can take an x out. And it leaves me with an x squared minus 4. Is that an irreducible quadratic? I hope not, because we don't know that case yet. Oh, I can factor it. The difference of 2 squared. My lucky day. So we get 3 distinct linear factors. I'm going to make linear now because that's so you can write. We're in case 1. 3 different. If I had some of the same, I could write them squared like I did with the x. If I had x plus 2 expression squared, well, that's like 1 linear factor repeated. They're not distinct, so that would be a different case. But here we're in this case. Case 1. I should probably say, a lot of time the textbook problems, they set up the details. The details are the polynomials here, so that to solve it, we're going to do a little bit of arithmetic. And the textbook problems, usually they're set up to be nice. But you just saw, I wasn't reading off my notes or anything. What we do in class, it may be a little bit messier. That just means we'll have fractions, maybe instead of integers, but that's okay. If we do the more complicated ones in class, you'll be, and the textbook does give us gentle problems, then you'll be better equipped. All right, so here's what we do. We need to find the decomposition. So we'll take our original function and we'll write it in factor form. We're going to decompose it, a constant over the first linear factor, another constant over the second one, and a third one over the third one. We're looking for those constants. We need A, B, and C.
How do you find those constants?
Well, let me tell you, William. There are a variety of ways. I'm going to show you what I think is the easiest way. Okay, and it only works. It works 100% of the time for case one. I can use it for some of the constants in case two, but not all. And that's also true for case three. So we're going to use it for all three of the cases we're going to talk about. But it's all we need to know for case one. All right. When I showed you the particular example that we started class off with, I emphasized the fact that we don't know the values of A, B, and C. We're going to find them. And when we do, this function is the same as that function. Right? We need them to be exactly the same function. So if I imagine taking the functions on the right and adding them up, the rules of adding fractions, which we learned way a long time ago, then I can get some information that will allow me to solve for the constants. So I really don't need to write this, but I'm going to. And now let's imagine finding a common denominator. Because they're all different, the common denominator is just the product of the three. And then this A, well, he's already over the x, so I'm going to add them up. I have to multiply them by x minus 2 times x plus 2. And the B is over the x minus 2. He gets multiplied by x and x plus 2. And the C gets only x and x minus 2. I promise that is exactly how your fourth grade teacher showed you to add fractions. Now, she didn't have variables in for he. It shouldn't be so gendered. He or she didn't have variables, but the process is exactly the same. Find the common denominator, multiply the fractions by 1 so that we have the same denominator. All right, and then what we're going to do is equate numerators. Because I need these to be exactly the same function. Since they have the same denominators, they must have the same numerator. And on the left, I have 2x plus 3. On the right, I have a times x minus 2 times x plus 2 plus b x plus 2 plus c x minus 2. So if those are going to be the same function, those have to be the same polynomial. Okay? For all x, they need to be the same polynomial. Now, I'm going to pick a value that makes the factors 0. I have 3 factors, so I'm going to pick 3 values, working my way through. The first one is, how do I make this factor x 0? I pick x equals 0. We're going to plug in a linear factor you can always make equal to 0. Right? And so we find the number that does the job. The numbers here are 0 and eventually plus or minus 2. And now just plug it in. Well, on the left-hand side, the 2x wipes out, I get a 3. What do I get on the right-hand side? If you plug in x equals 0.
-4a.
Negative 4a. Right, this x wipes out this term, and this one wipes out that one, but none of these get wiped out. We get -2 times 2, -4, and therefore, what's the magic number for a?
-4.
Yeah, so that's why I was talking earlier, probably in the textbook, we may get integers all the time, but hey, we can handle fractions. Now, that's one of my constants, it's a, but we know we still need to know b and c, so we're just gonna plug in another number. That makes it a factor 0. What's a good one, Scott?
1.
There's a better one. 2. Because it makes this factor 0. What do you get on the left?
7.
7. What do you get on the right? 8b. So 2 makes this 0, so that guy's gone. It makes this 0, that guy's gone. And then I'm going to have plug in a 2, and then plug in 2 gets me 2 plus 2. 4 times 2?
B equals 7/8.
Pardon?
B equals 7/8.
7/8. And finally, what number should I plug in? -2. What do I get on the left?
-1.
-1. On the right, this guy goes away, that guy goes away. I get 8c plus 8c, right? We're plugging a -2 in here, and a -2 there makes -4. So -2 times -4 is 8. So c is -1/8. Got him. And if you believe the system, it's not that hard, right? You have linear factors. There is an x value that makes it 0 because we need the numerators to be true for all values of x. They need to be exactly the same polynomial. We can just plug them in. Now, where's the problem? Did I erase the problem? Yeah. Let's solve it. We were looking for the antiderivative of 2x plus 3 divided by, I guess I won't factor the denominator. We'll look at the problem the way we originally saw it. Because we have linear factors in every denominator, every antiderivative is a log. So we have the constants, a, -3/4. We can bump that out, and then we get the log of just x. And then we get b plus 7/8.
And we multiply by log of x minus 2.
Plus, or actually minus. C was negative, right? ln plus 2. And for good measure, we'll add a c. Is that clock right? Man, time flies. Can I say one more thing? It'll help you with your with the homework. And I'll think good thoughts about you for letting me go late. I think we can skip this step completely, especially in case 1, and we can just go right from here to where we equate the numerators. Right? We're going to take a and multiply it by that and that. We're going to take b and multiply it by that and that, and c by those, and I can just write those out. I don't think we really need to write this step out. Okay? Maybe you need to on the first one, you decide. But I think in the end, we can skip that step and just focus on those numerators. We're going to make the denominators the same, so the numerators have to be the same. Have a wonderful weekend and see you Monday.